Hi guys, so today we're going to be looking at Chapter 8, Section 1, Defining and Using Sequences and Series Part 1. So we're going to start off first with the problem of what is a sequence? A sequence is an order of list numbers. So we are going to be given a function and we're going to be sequencing them from 1 all the way through the value n. So for example, if we were asked to write the terms of the sequence of the following function, negative 3n, or to the power of n minus 1, all I'm going to do is I'm going to take my n value, which is 1, 2, 3, 4, and 5, and I'm going to substitute it into the n value. So instead I get negative 3 to the power of 1 minus 1. That equals to negative 3 to the power 0, which is just 1. And again, negative 3 to the power of 2 minus 1. That equals to negative 3 to the power of 1, which equals to negative 3. Again, negative 3 to the power of 3 minus 1. That equals to negative 3 to the power 2, which is 9. And then we'll do it again. Negative 3 to the power of 4 minus 1. That would equal to negative 3 to the power of 3, which is negative 27. And we have here negative 3 to the power of 5 minus 1. And so that gives us negative 3 to the power of 4, which is 81. And again, I'm going to stop at the fifth one because we're only asking for the first 5 terms. So these are my following values that I would receive for the following sequence. Okay. So basically what we're doing is we're following based off of a rule, but what we're going to be looking at now is the sequence itself, and we're writing a rule for it. So the best way to do this, and it doesn't work all the time, but most of the time you can go by this rule. You want to figure out first to see if you can find the difference between all these numbers. So I'll start off and see if I can add or subtract anything. If adding and subtracting doesn't work, then I'll try multiplying or dividing. So I do know that 2 to 9, I could add 7. 9 to 7, I could also add 7. Oops. Add 7. 16 through 23, add 7, and so on. It seems like all of them, you can add 7 to every single number. So if that's the case, then I want to use the following rule, where I'm going to be getting 7, multiplying it with n, and either I'm going to be adding a number or I'm going to be subtracting a number to it. So 7n minus some form of number. I don't know yet. I just need to check it out first before I figure that out. So if I have here 7 times 1, and I will do 3 sequences. So I'll do it when a is equal to 1, a equals to 2. We get here 7 times 2. And we have here 7 times, or a3, the third term, 7 times 3. I want it to equal to the first 3 terms of my sequence. So no matter what, 7 times 1 has to equal to 2, 7 times 2 has to equal to 9, and 7 times 3 has to equal to 16. So it's definitely not going to be adding, because that would make this number have to be bigger than 7. It seems like it's subtracting, and it seems like I can subtract by 5. So let's see and test it out for the other two. Let's see if that works as a pattern. 7 times 2 is 14. And then 14, that would be minus 5. 7 times 3 is 21. Minus 5 would give us 16. And so that would be our final pattern that we could use to continue on our sequence. So they asked us to write also the next term and the rule. The rule first that we have is that an is going to be 7 times n minus 5. That would be our rule that we would be following for this type of sequence. So they also wanted to ask for the next term. We have our terms given to us. We have our first one, second one, third one, fourth one, fifth one, sixth one, and we need our seventh term. So my seventh term here would be a7 equals to 7 times 7 minus 5, which would give us 49 minus 5, which would be 44. So that would be our final sequence, or the next sequence over. Okay. Alright, let's try out the next problem. Writing a rule for sequences, but this time the difference is not going to be by adding or subtracting. In this case, we have multiplying. If you notice here, 1 times 3 gives us 3, 3 times 3 gives us 9, and so on. And it seems like we're always using multiples of 3. So if the difference, or like the change, is multiples, I want to use exponential powers. So 3 to the power of n plus something should equal to it, or 3 to the power of n minus something should probably work for it. So if I were to try this out, if I have here 3 to the power of 1, and this is going to be for a1. Again, I want it to equal to 1 in the end, which seems to be minus 1, because 3 to the power of 0, that would equal to 1. Let's test it out for the second one. We have here a2, 3 to the power of 2. Let's see if that equals to 3. So if I minus 1, that seems to work out, because 3 to the power of 1 equals to 3. And then a to the power of 3, 3 to the power of 3 minus 1. That does equal to 9, which is cool. So, seems like the formula that we're going to be using for a to the power, or a of n, is going to be 3 to the power of n minus 1. That would be the formula that we would use for the sequence. So the only number that we want that's next is the first term, second term, third term, fourth term. Seems like the fifth term is the one that I want in this case. So right here I have a base 5, 3 to the power of 5 minus 1 equals to 3 to the power of 4, which is 81. There you go. Okay, so the next one, writing the next term and writing a rule for nth term. So if I want to do this, whenever you see first that there is an alternation of positive to negative, then positive, then negative, then positive, then negative, you always want to use the formula -1 to power of n plus 1. Because if I were to use power of 1 here, that would give us, or sorry, the first term, then we get -1 to the power 2, which would make your number positive first. Then, after that, 2 plus 1, if you were to change it, -1 to the power 3, that would turn your number into being negative. So it's always good to use this formula, and it's always going to be multiplying with whatever your function is going to be here. Okay, next thing to also think about is, if you notice on the fraction, the only thing that seems to be the most consistent are the 3s. The only time there's not a 3 is with these 1 values. And so what I want to do before I do anything is make sure that I change these 1s into 3s first. And we can do that by multiplying 3 to both the top and the bottom of the fraction. That way we have something that's more consistent with each other, at least on the top of the number. So we get 3 over 5, negative 3 over 7. Then we have 3 over 21, negative 3 over 11, 3 over 13, negative 3 over 15. Okay, so now that we have more consistency on the top, seems like no matter what, our fraction is always going to be 3, and then something happens afterwards on the bottom. On the bottom, if we were to focus on the denominator, seems like there is a pattern showing with 5 and 7 and 21 and so on. If I were to look at the pattern, oops, sorry, that was supposed to be not 21 but 9. If I were to look at this pattern here, you could see that they're all adding by 2. So 5, then 7, then 9, then 11. All of them add by 2. They just all are increasing by 2 points, 2 points, 2 points. Plus 2, plus 2, plus 2. And if you notice from not this one, but this one over here, if you're increasing, we want to try using one of these two rules, where whatever you're adding is going to multiply with n, and we're either going to add a number or subtract another number consistently. So, in this case, we have here 2n, and it has to equal to plus or minus 5. Okay, so this is going to be the first term, so 2 times 1. For it to equal to 5, we would have to add 3. So for the second one, 2 times 2. The second term was 7. That also would be 2 times 2, which is 4. So I would also have to only add 3. And it seems like it's working because right here, 2 times 2, or 3, equals to 9. I would also have to add 3 as well, because it's just 6 plus 3 equals to 9. So at least we know what the new formula should be. We should have 2 times n plus 3 as our bottom factor, along with multiplying the negative sign, negative 1 to power of n plus 1. And so that would be your final answer. Last part, just finding the extra term. So we have 1, 2, 3, 4, 5, 6 terms. We're looking for our 7th one. So when the 7th term, we would get 3 over 2 times 7 plus 3 times negative 1 to the power of 7 plus 1. And that equals to 3 over 17 times negative 1 to the power of 8, which does become 3 to the power of 17. Cool. And so that would be our final answer. So hopefully this helped. Most of the time this rule works. Sometimes you are going to have to get a little creative and do something else different, but majority of the time this should be helpful. So hopefully this helped. Good luck.